Hey guys, my name is IBM and I'm still recording quantum physics lessons for my students. So this is Physics 9702. This is paper 4 and the topic we are dealing with is quantum physics, and this is going to be a lesson 2. So I want to take you to lesson 2. Just like I mentioned in quantum physics, most of the things here are simply facts. Which facts we have to resonate with, or which facts have to resonate with our minds uh, for us to be able to understand quantum physics as a topic. So in lesson 2, we are going to talk about the introduction to photoelectric emission. So let's go. So we are talking about photoelectric emission. Of course, the photo comes from light. So immediately when someone sees photo, the first thing to come into their mind is light. Just to give you a background, we know that electrons in a metal conductor are free to move around in it. So we know that metal conductors have free moving electrons. These electrons can move from one end of the conductor to another end of the conductor. And according to the concepts we studied in electricity, it is these free electrons that form the electric current. That's why we define electric current as the rate of flow of these charge carriers. So it is these free electrons that form the electric current when a potential difference is applied across the ends of a metal wire. However, to remove free electrons from metal requires energy. Even though these electrons are free to move within the metal, to remove them from the metal would require energy. Simply because even though they are free to move within the metal, they are held by the electrostatic attraction force from the positively charged nuclei within the conductor. So to remove them completely from the metal conductor, then this would require energy. So if these electrons are exposed, if an electron is able to escape from the metal surface, that means work must be done against the electrostatic force of attraction, which is keeping them closer to the positively charged nuclei. So the electron must therefore gain energy. The electron must be given some energy, and if we give the electron energy by illuminating the metal conductor with light, or if this energy given to the electron is in the form of light energy, then the phenomenon is going to be called the photoelectric emission. So the electrons from a metal conductor to be completely lost or to be completely released from the metal conductor would require energy. These electrons require energy because work must be done against the electrostatic force of attraction between these electrons and the positively charged nuclei within the conductor. If we supply energy to release these electrons by illuminating the conductor with light energy, then the process by which these electrons are released is going to be called photoelectric emission. Of course, photo is coming from light. But of course, not any light is going to cause emission of the electrons, as we shall see. It is going to be light which has high enough energy. Remember, we said in lesson 1 that the energy of light, or the energy of a photon, is given by hf. Now, if light has several photons, that means the total energy of light is going to be n times hf, where n is the quantum number because energy is a multiple of a specific value, or energy of electromagnetic radiation is going to be a multiple of the smallest energy of a single photon, which is hf. So the electrons must be given energy to overcome or to break the electrostatic attraction force between the electrons themselves and the positively charged nuclei. So this process is called photoelectric emission, and therefore we should define photoelectric emission as the release of electrons from a metal surface when exposed to an electromagnetic radiation, which is now light, of high enough frequency. The term high enough frequency is very important because not all light will cause electrons to be released from the metal surface. The light which is able to release an electron from a metal surface should have high enough energy. That's why we are saying the release of electrons from a metal surface when exposed to an electromagnetic radiation of a high enough frequency is what we call photoelectric emission. High enough frequency means high enough energy. So the photons must have high enough energy to cause electrons to be released from a metal surface. To understand this, let's talk about a simple demonstration which can help us to understand this. So to demonstrate the photoelectric emission, an experiment with a charged gold leaf electroscope can be performed. We know what a gold leaf electroscope looks like. So a gold leaf electroscope looks like this. This is just a simple picture to show how a gold leaf electroscope looks like. Every school must be having a gold leaf electroscope. So let's assume we have a freshly cleaned zinc plate, which is placed on top of a negatively charged gold leaf. Let's say this is a gold leaf which had been charged negative. And then on the zinc plate, of the gold leaf electroscope, let us assume that a freshly cleaned zinc plate is placed on top of the negatively charged gold leaf electroscope as shown here. So we bring a zinc plate which is negatively charged and we place it on the top of the gold leaf electroscope as shown. Remember, the gold leaf had already been charged negative. So because the gold leaf is negative, if we illuminate the zinc plate with light, then if photoelectric emission occurs, we would expect that the gold leaf would move far away from the rod, the rod of the gold leaf electroscope. So the initial position of the gold leaf is this one, where if we bring a negatively charged zinc plate, it means negative charges are flowing through the rod, and because the gold leaf had already been negatively charged, then they are repelling each other, so it has been repelled. This is the initial position. But then, if we illuminate the zinc plate with light, as shown in the second diagram, let us now illuminate the zinc plate with light so that electrons are knocked out of the zinc plate as shown by this diagram here, which means now electrons are being lost by the gold leaf electroscope, and that means this rod here becomes less negative, and therefore the gold leaf is going to be seen to collapse. So collapse of this gold leaf indicates that the repulsive force between the leaf itself and this rod has reduced, simply because the negative charges which were flowing through the rod are now being lost to the surrounding. That is what we call photoelectric emission. Uh, in schools where it is possible to charge a given rod negatively, this experiment can easily be conducted. Unfortunately, the source of ultraviolet radiation may not be easily found in school, but this can be demonstrated by a video to students in class. So a freshly cleaned zinc plate is placed on top of a negatively charged gold leaf electroscope. And if the leaf is negatively charged, and yet we have brought a negatively charged zinc plate, it means the negative charges from the zinc plate are flowing through the gold leaf the rod here, the metal rod here, which makes the gold leaf to be repelled because they have like charges. But if visible light of any color is shown on the plate, the leaf is seen not to move at all. Why? Recall the definition of photoelectric emission. Electrons are only released when electromagnetic radiation has high enough energy. So for a zinc plate illuminated with visible light, we don't see the gold leaf collapsing, which means visible light does not have enough energy to cause electrons to be emitted from the zinc plate. Even when when I talk about intensity from light, remember intensity would refer to brightness. At this point, intensity is going to be referring to the number of photons. So even when the intensity, that is the brightness of the light, is increased, the gold leaf remains in its deflected position. So intensity does not cause the gold leaf to collapse if the light which is used does not have high enough energy. So it means the intensity has no effect as long as the light used or the light shining on the metal surface does not have enough energy. However, in B, when ultraviolet, that is light, when ultraviolet radiation or light is directed onto the zinc plate, the leaf is seen to gradually fall or to collapse. So why is it collapsing with a visible why is it not collapsing with a visible light but is collapsing with ultraviolet light? If you remember the electromagnetic spectrum, that is Ruben Reed's mother is visiting Uncle Xavier's garden. Notice that if this is visible light and this is ultraviolet, ultraviolet light has higher frequency than visible light. So ultraviolet light has more energy than visible light. So it's like the minimum energy required to release an electron from a zinc plate is within the ultraviolet. It is not in the visible light. So when ultraviolet radiation or light is directed onto the zinc plate, the leaf is seen to collapse gradually, as shown in diagram 2. So this collapse of the leaf is because electrons are being ejected from the zinc plate, making the charges or the negative charges within the metal rod to reduce, which means the repulsive force between the gold leaf itself and the metal rod reduces and the gold leaf collapses. So this collapse of the leaf shows that the electroscope and the zinc plate have both lost charge, and this charge is due to electrons emitted by the plate being repelled away. So the electrons which were ejected from the zinc plate have been repelled to the surrounding, and they have left the apparatus. Therefore, there are fewer negative charges remaining, so the repulsion decreases. That's why we see the gold leaf collapsing gradually. So this is the phenomenon of photoelectric emission, and the electrons are always going to be called photoelectrons, or we shall be calling this the movement of these electrons or the ejection of these electrons. We would call it a photocurrent with time. And we have also seen that with intensity of visible light being increased, because visible light could not eject electrons from the zinc plate, there was no effect. But if the intensity of ultraviolet radiation is increased, the leaf falls even more quickly. Remember, increasing the intensity would be equivalent to increasing the brightness, but increasing the intensity simply refers to increasing the number of photons incident on the zinc plate. So it's like increasing the number of photons incident on the zinc plate makes more electrons to be ejected from the zinc plate. So it's like increasing the intensity of ultraviolet radiation increases the rate at which electrons are being ejected from the metal surface. So if the intensity of ultraviolet radiation is increased, the leaf is seen to fall more rapidly or more quickly, showing that the rate of emission of electrons has increased. Therefore, the rate of emission of electrons is directly proportional to the intensity as long as the incident radiation has high enough energy. As long as the incident radiation has enough energy. I want you to note the difference between visible light and ultraviolet, as I've mentioned earlier on. The difference between ultraviolet radiation and visible light is that ultraviolet radiation has a shorter wavelength and a higher frequency than visible light. Just like I've just mentioned from Reed's mother is visiting Uncle Xavier's garden. That is the electromagnetic spectrum. Moving from radio waves to gamma rays, the wavelength is decreasing. So ultraviolet has a shorter wavelength. But again, moving from radio waves to gamma rays, the frequency is increasing, which means ultraviolet has a greater frequency. And remember, the energy of electromagnetic radiation depends on the frequency. So with a higher frequency, ultraviolet has a higher amount of energy. So the energy of ultraviolet light is high enough to cause emission of electrons from a surface of zinc plate. Of course, it doesn't mean that ultraviolet will cause emission of electrons from all from metals of different nature. It might be enough for zinc, but it may not be enough for sodium. It may not be enough for other metals. So that is what we are meaning. That's what we mean by photoelectric emission: release of electrons from a metal surface when electromagnetic radiation of high enough energy is incident onto the metal surface. Of course, there were several other further investigations that can be carried out in a modern laboratory. So further investigations with such apparatus that we have just explored above using the gold leaf electroscope could lead to several conclusions, which could include: number one, if photoelectric emission occurs, it does so instantaneously. Observations show that if ultraviolet light is shined on the zinc plate, the gold leaf immediately starts collapsing. What does that mean? If emission occurs, it occurs instantaneously. In other words, there is no time delay between illumination and emission. There is no time delay between shining ultraviolet light onto the zinc plate and collapsing of the gold leaf, which means there is no time delay between shining of the ultraviolet light onto the zinc plate and emission or release of electrons from the zinc plate. So whenever photoelectric emission occurs, it does so instantaneously. Number two, photoemission occurs only if the frequency of the incident radiation is above a certain minimum value, which we shall later on call the threshold frequency. The reason as to why the gold leaf could not collapse is because the reason as to why the gold leaf could not collapse with the visible light is because visible light frequency is low. In fact, it is because the frequency of visible light is below the minimum required to cause the release of electrons from a metal surface. The frequency of ultraviolet light is above the minimum required to release an electron from the zinc plate. So, photoelectric emission only occurs if the frequency of the incident radiation is above a certain minimum value, which we call the threshold frequency. Therefore, there is a threshold frequency below which no emission of electrons occurs from a metal surface. And I said we may not use ultraviolet for all the metals. Some metals for ultraviolet radiation may not be enough. The frequency of ultraviolet radiation may not be enough to cause emission of electrons from some other metals, but is enough for the zinc plate or for zinc surfaces. So that means different metals will have a different minimum frequency below which no photoelectric emission occurs, as we shall see. Number four, whether or not emission takes place depends only on whether the frequency of radiation is above threshold. It does not depend on the intensity of the radiation. That's why we saw that even when we change the intensity of visible light for a zinc plate, there was still no emission. Emission does not depend on the intensity of the radiation. The intensity just affects the rate at which emission occurs. But emission will not occur if the frequency is below the threshold. So whether or not emission takes place depends only on whether the frequency of the radiation is above the threshold for that surface. It does not depend on the intensity of the radiation. And for a given frequency, that is, if the frequency is already above threshold, then the rate of emission of photoelectrons is proportional to the intensity. So for the intensity just affects the rate of emission, the rate at which photoelectrons are emitted. But of course, if the light has frequency below the threshold, there is already no emission. But if light is of frequency above threshold, there is emission, and then the rate of emission will depend on the intensity. So intensity just affects the rate, or the rate of emission just depends on the intensity. But emission itself does not depend on intensity. For emission to occur, it doesn't depend on intensity. It depends on the threshold frequency. And all these above conclusions, all the above observations and conclusions from photoelectric emission provide evidence for what we shall call the particulate nature of electromagnetic radiation. Emission occurring instantaneously, there being a threshold frequency, the rate of emission depending on intensity, all these observations are going to be providing evidence for the particulate nature of electromagnetic radiation. In other words, electromagnetic radiation having particle-like behavior, as we shall explore in more details later on. Let's talk about the stopping potential. So another experiment using the apparatus below, we can use this apparatus here, where on one side we have an emitter which is going to emit, we expect it to emit electrons when illuminated by maybe light. This could be a zinc plate. Let's say this is an emitter which could be a zinc plate. And let's say incident light which is not visible light, but let's say because this is zinc, let's say this is UV light incident on the zinc plate. On the other side, we are going to have a collector where we expect the electrons to move to. So this could be a vacuum. This could be an evacuated tube. So on one side of our tube where we have our emitter, we have connected to a positive potential, and on the other side we have connected this to a negative potential. So if ultraviolet light or light of enough frequency is incident on the zinc plate, we expect the electrons to be ejected from the zinc plate, and we expect them to move towards the other end. But note that this is at negative potential, yet electrons are also negatively charged. So this is at positive potential and electrons are being ejected from the zinc plate. It is at positive potential because it is connected to the positive terminal. This is at negative potential because it's connected to the negative terminal. So if ultraviolet radiation of a fixed frequency, which is of course above the threshold, frequency is fixed but above threshold, is shown to the metal surface A, we expect this to emit what we shall call photoelectrons. They are called photoelectrons because they are ejected as a result of shining light onto the metal surface. Some of the emitted electrons will travel from A to B. And if the electrons travel from A to B, the circuit is going to be complete and the microammeter will register a current. So in other words, a current is going to be registered in the microammeter. Now, if this is an adjustable PD supply, this is a variable power supply or an adjustable PD supply, the electrons with high enough energy are going to overcome the repulsion from the negative potential this side and will reach this point and the current flows. And of course, we know that current flows from positive to negative. And if there is a current, if we adjust the potential difference and increase, make this even more negative, it means the repulsive force between the negative potential on B and the electrons is going to be increased. So if a PD is applied between A and B, with the B negative with respect to A, any electron moving from A to B is going to gain what we call electric potential energy as it moves against the electric field. Because this is positive, this is negative, the electric field is in that direction. An electron is naturally supposed to move in the other direction. So if the electron moves from A to B, yet it is supposed to move towards the positive potential or towards the positive plate, then it is moving against the electric field. In other words, the electron gains what we call electric potential energy. So the gain in electric potential energy is at the expense of the kinetic energy of the electron. So as the electron moves from A to B, it loses kinetic energy. So I'll say the loss in kinetic energy is equal to the gain in electric potential energy. Because it is moving against the field, work is done It is moving against the force of repulsion. It means it's gaining electric potential energy. And remember from other chapters or from electric fields, we saw that electric potential energy is the charge times the potential difference between the two plates. So it means that a half m v squared is going to be equal to the charge times v. So if the voltage between A, if we increase the voltage between A and B, if the voltage between A and B is gradually increased, it means the force of repulsion from B is also increased, which means the current registered in the microammeter goes on decreasing because electrons experience more repulsion from B, and therefore most of them may not be able to reach point B. As we adjust the PD between A and B, a point is going to reach where the microammeter reads 0. That means almost no electron ejected from A has high enough energy to reach point B. At that point, a potential difference between A and B has been established, which does not allow any electrons ejected from A to reach B. And that potential difference which has been established is what we are going to call the stopping potential. So in a nutshell, I've just said that if ultraviolet radiation of a fixed frequency, which is of course above threshold, is shown to the metal surface A, it emits photoelectrons. And I said some of these emitted electrons travel from A to B, and if electrons travel from A to B, the circuit is going to be complete, and we expect the microammeter to detect a current. It is microammeter because the current we expect to detect is very, very, very small. So we use a microammeter. If a PD is applied between A and B, where B is negative with respect to A, any electron moving from A to B, we said it gains a potential energy, which is actually electric potential energy because there is an electric field between A and B. And I mentioned that naturally, electrons move towards the the positive potential. But now that they are ejected from the positive plate and they are moving towards B, they are moving against the field. In other words, electrons naturally are supposed to experience a force in that direction because they are repelled by the negative plate. So the force on the electron is in that direction, but the electron are moving towards B. So it means they are gaining electric potential energy. Just like you could lift an object above the Earth's surface, you're moving the object against the gravitational pull from the Earth. So the object gains gravitational potential energy. Even in this case, the electron is moving against the force acting on it, which is the electric force. Therefore, the electron gains the electric potential energy. So the gain in the electric potential energy is at the expense of the kinetic energy of the electron. So we say the electron loses kinetic energy as it gains electric potential energy. And of course, the electric potential energy will be the charge of the electron times the potential difference, or the PD between A and B. In other words, a half times the mass of the electron times its speed squared is equal to charge times the potential difference. So many times you will see us using kinetic energy as being E times V or QV for an electron in an electric field, as we saw in the electric field topic. So if if the voltage between A and B is gradually increased, like I mentioned, the current registered on the microammeter decreases and eventually falls to 0. And when it falls to 0, we said a stopping potential between A and B has been established. Therefore, we can define the stopping potential as the minimum value of potential difference necessary or required to stop the electron flow. The minimum value of the potential difference necessary to stop the electron flow. That is called the stopping potential. It is the minimum potential applied between electrodes to reduce the photocurrent in the circuit to 0. Because as we adjust the voltage between A and B, a point reached when the current in the micrometer eventually goes to 0. It means the photocurrent has gone to 0. Since no more electrons can flow from electrode A to electrode B, then we say the photocurrent has gone to 0 because the microammeter will not register any reading. So the minimum potential applied between electrodes to reduce the photocurrent in the circuit to 0 is what we are going to define as the stopping potential. So when the stopping potential has been established, it means the electrons or an electron has lost all its kinetic energy, or its kinetic energy has lost all its kinetic energy and has gained electric potential energy. Therefore, the loss in kinetic energy, like we have mentioned earlier on, is equal to the gain in electric potential energy. So this measures the maximum kinetic energy with which the photoelectrons are emitted. It therefore follows that the maximum kinetic energy of electrons is equal to E times Vs, where Vs is going to be the stopping potential, and this means that I have mv squared max equals to EVs, where V squared max is the maximum speed of the electrons. So if we want to determine the maximum speed an electron can have, then we just make Vmax the subject, and this is what we obtain. So just like we knew from other topics, the energy of a photon is extremely going to be very small. That is, it is going to be far less than a joule. We have seen some of these in lesson 1, that the values of energy for photons were always of the order 10 to the power of minus something, 10 to the power of minus 19 joules, minus 11 joules, and so on and so forth. So the energy of a photon is extremely small. We may not always use the unit joule as the unit for the energy of a photon. It means another convenient unit may now be established, because the unit joule will be quite clumsy to be used for the energy of a photon. So when an electron travels through a PD, energy is transferred, and you remember PD is equal to the energy transferred per unit charge. And that means the energy transferred is equal to the charge times the PD. So if an electron which has a charge of 1.6 times 10 to the power of minus 19 coulombs is transferred or travels through a PD of 1 volt, then its energy change is given by 1.6 times 10 to the power of minus 19 joules times 1 volt. So this is an electron and this is a volt. So this gives us 1.6 times 10 to the power of minus 19 joules. So it appears as if one charge of an electron times 1 volt is the same as 1.6 times 10 to the power of minus 19 joules. So it means the electron volt is going to be a convenient unit to be used for the energy of a photon. For those who have already studied nuclear physics, you have seen the unit electron volts there. So the electron volt is the energy transferred when an electron is accelerated through a potential difference of 1 volt. The electron volt is a unit for energy. It is the energy transferred when an electron, that is 1 electron, is accelerated through a PD of 1 volt. 1 electron times 1 volt. That's what we call the electron volt. So many times you'll use 1 electron volt as being equal to 1.6 times 10 to the power of minus 19 joules, especially in calculations. 1 electron volt as 1.6 times 10 to the power of minus 19 joules. So this unit of electron volts is quite convenient for very small quantities of energy of a photon. So thus, we can therefore use this as the basis for the definition of the electron volt. So define the electron volt as the energy transferred when an electron is accelerated through a potential difference or a PD of 1 volt. Thus, another energy unit, the electron volt, is going to be more useful for amounts of energy smaller than 1 joule. So for most of the energy smaller than 1 joule, we shall use the unit electron volt. Hence, to convert energy from electron volts to joules, we shall always multiply by 1.6 times 10 to the power of minus 19, as we did in nuclear physics. And also to convert from joules back to electron volts, we shall just divide. Electron volts to joules, we just multiply. Joules to electron volts, we shall be dividing. You should be now comfortable with converting either way. And also do not forget that the loss in kinetic energy, which is a half mv squared, was equal to the gain in electric potential energy, which is E times capital V, and we obtain the speed from V equals the square root of twice EV over m. This equation applies to any type of charged particle, including protons and ions, and we shall also employ this equation in magnetic fields. The loss in kinetic energy is equal to the gain in electrical potential energy, or the gain in kinetic energy can also be equal to the loss in the electrical potential energy. I want people to note the fact that there is a current in the micrometer at voltages less than stopping potential indicates that there is a range of kinetic energies for these electrons. Initially, before we reach the electric potential, there was a current in the microammeter, which means some electrons had enough kinetic energy to overcome the force of repulsion, and they were able to travel from plate A to the collector B. Some electrons had enough kinetic energy to travel from A to B as we went on increasing the potential difference between A and B until a point when there was completely no electron reaching point B. That's when the current became zero. So it means electrons therefore have different kinetic energies as they are ejected from the metal surface. There is a reason as to why they have different kinetic energies. Perhaps not all electrons reside on the surface of the metal on the surface of the zinc plate. And since not all of them reside on the surface of the zinc plate, when light is incident onto the zinc plate, the electrons which are on the surface would require less energy to become free, but the electrons which are below the surface will require some energy to come to the surface, and that means the surplus which they will have as kinetic energy becomes smaller. So it means there is a range of kinetic energies for these electrons when they are ejected from the metal plate. That's why the microammeter had a current at voltages less than the stopping potential. There is a range of kinetic energies for these electrons. If the experiment is repeated with radiation of greater intensity but the same frequency, intensity is changing but the frequency is constant, then the maximum current in the micrometer increases, but the value of the stopping potential is unchanged. So the current is increasing, or the maximum current in the micrometer is increasing, but the value of the stopping potential is not changing. Why? So it's like increasing the intensity, but without changing the frequency, does not affect the kinetic energy of the electrons. However, the stopping potential, the micrometer reading increases because it's like there are more electrons, because current is the rate of flow of charge carriers. So the micrometer reading increases because it's like there are more electrons being ejected from A to B. But the value of the stopping potential is unchanged because the value of the stopping potential is depending on the loss in the kinetic energy. So it's like the kinetic energy of the electrons is not depending on the intensity, but is going to be depending on the frequency. And because the frequency is the same, the kinetic energy of the electrons is not changing. And if the kinetic energy of the electrons is not changing, then it makes sense that the stopping potential is not going to be changing. But because the intensity has been increased, it means more electrons are ejected from the metal surface. And since the current is the rate of flow of these electrons, since there are more electrons, it means the micrometer reading must increase. Okay, we shall explore that in more details later on. Simple self-check. A proton in bracket charge positive 1.6 times 10 to the power of minus 19 coulombs. The mass is given as 1.7 times 10 to the power of minus 27 kilograms, is accelerated through a potential difference of 1500 volts. Determine its final kinetic energy in joules and its speed. So, of course, if it is accelerated through a potential difference of that, we have said that the kinetic energy is going to be equal to half mv squared, which is going to be equal to the charge times the accelerating PD. So this is going to be, the kinetic energy is going to be equal to the charge, which is 1.6. I want to write Q instead of E because it's a proton. 1.6 times 10 to the power of minus 19 times the accelerating speed, which is 1500. So from my calculator, I have 1.6 times exponent minus 19 times 1500. So the kinetic energy is 2.4 times 10 to the power of minus 16 joules. Of course, this is a very small energy, so the unit joules might not be good enough. If you want this to be in electron volts, you just say 2.4 times 10 to the power of minus 16 divided by 1.6 times 10 to the power of minus 19, because we said from joules to electron volts we divide, from electron volts to joules we multiply. So that is answer divided by 1.6 exponent minus 19. Remember, 1 electron volt is the same as 1.6 times 10 to the power of minus 19. So this is the same as 1500 electron volts. If we wanted it in joules, this would be the answer. If it was in electron volts, it would be just 1500 electron volts. Then its final speed, so I have mv squared equals to charge times v. So the speed is going to be twice the kinetic energy divided by m under the square root. So twice the kinetic energy is qv, so this is the square root of 2 times 2.4 times 10 to the power of minus 16 divided by the given mass, which is 1.7 times 10 to the power of minus 27. I'll check this with my calculator. 2 times 2.4 exponent minus 16 divided by 1.7 exponent minus 27. Then square root. So this is 5.3 times 10 to the power of 5. Okay. That is just for us to be able to use the equation loss in kinetic energy equals to gain in electric potential energy, or loss in electric potential energy equals to the gain in kinetic energy. Let's talk about the graph of kinetic energy against frequency. Remember in a previous slide we mentioned that when the intensity was increased with the previous experiment of an evacuated tube, which we call it a photocell. When the intensity was increased with the frequency remaining the same, we saw that the current was increased but the stopping potential did not change, which means increasing the intensity does not change the kinetic energy of the electrons, but increasing the intensity, as long as the frequency is above threshold, increasing the intensity just increases the rate of emission of electrons, which increases the photocurrent. So it's like the maximum kinetic energy does not depend on the intensity, but it depends on the frequency, and therefore it is directly proportional. So the above experiment can be repeated using ultraviolet radiation of different frequencies, measuring the stopping potential. So we have now seen that the frequency is what can affect the stopping potential. If the frequency is kept constant, the stopping potential does not change. And remember, a half mv squared was equal to the charge times the accelerating PD. And we have seen that it is the frequency which affects the stopping potential. The frequency affects the energy of the photons, and it is the energy of the photons which is given to the electrons. So the frequency affects the energy of the photons, which energy of the photons is given to the electrons, and the energy of the electrons affects the stopping potential. So the above experiment can be repeated using ultraviolet radiation of different frequencies and measuring the stopping potential of each frequency. And when the maximum kinetic energy of the photoelectrons is plotted, when the graph of maximum kinetic energy of the photoelectrons is plotted against the frequency, the graph which is obtained looks like this. The maximum kinetic energy is directly proportional to the frequency. But this graph does not go to zero because there is a minimum frequency below which no photoelectrons are emitted. So this graph has an x-intercept. There is a minimum frequency that we mentioned earlier on, below which no photoelectric emission occurs. So as we go on increasing the frequency, there is only emission above the threshold. Below the threshold, there is no what? There is no emission. That's why our graph starts from a certain value on the x-axis. Our graph starts on a certain value on the x-axis, and it is going to be a straight line because increasing the frequency above the threshold, the stopping potential increases, which means the maximum kinetic energy of the electrons also increases. Okay, so the photoelectrons have a range of kinetic energies, which I've already mentioned, that is from 0 up to some maximum value. If f, the frequency, is increased, the maximum kinetic energy of the photoelectrons also increases. For a constant f of the incident radiation, the maximum kinetic energy is not affected by the intensity, as we saw earlier on. When we increase the frequency and we kept when we increase the intensity and kept the frequency constant, the maximum kinetic energy was not affected. But if we increase the frequency, as long as the frequency is above threshold, the maximum kinetic energy of photoelectrons also increases, which affects the maximum, which increases the stopping potential. So when the graph of the figure above is extrapolated to a point where the maximum kinetic energy of photoelectrons is 0, then the threshold frequency may be obtained. So many times we shall have graphs which will be hanging in space like that. And if we want to determine the frequency for which the maximum kinetic energy of electrons is 0, then we shall prolong this to the x-axis. Where it cuts the x-axis is the frequency for which the maximum kinetic energy of the electrons is 0, and this frequency is called the threshold frequency. At this point, the electrons have been released from the metal surface, but they don't have energy to move away from the metal surface, so they remain hanging around the metal surface. That frequency is what we call the threshold frequency. So we are saying that the frequency of electromagnetic radiation affects the maximum kinetic energy of the electrons, but the intensity does not affect the maximum kinetic energy of the electrons, neither does it affect the stopping potential. The intensity just affects the rate at which electrons are being emitted from the metal surface. So it's like more photons incident on the metal surface, that is increased intensity, more electrons are going to be ejected from the metal surface. So intensity affects the rate of emission of photoelectrons. It affects the rate, it affects the photocurrent, because photocurrent is the rate at which these electrons are being emitted. Okay, then let's now try to compare the wave theory and the photon theory. So before the study of photoelectric effect that we have just talked about here, people believed that light was actually wave motion. Because there was evidence proved by or provided by Young's experiment, that is interference patterns, and there was also diffraction effect. Diffraction and interference were evidence that light was a wave. However, conclusions that we have just seen from photoelectric emission produced some doubt as to whether light is a continuous wave as predicted by the wave theory. In fact, one major one is the presence or the existence of the threshold frequency. If light is a continuous wave, when we shine light on a metal surface, why can't we shine visible light on a zinc plate for a long period of time and electrons are emitted from the zinc plate? If light is a continuous wave, why is that when we shine light for a long period of time, or even if we increase the intensity of light falling on the metal surface, such as zinc, if the light has a lower frequency, even if we shine light for a long period of time, no photoelectric emission occurs? So the existence of the threshold frequency started bringing problems and concerns about the wave theory of light. So the classical wave theory predicts that when electromagnetic wave, that is light, interacts with an electron, the electron will absorb energy from it. So if an electron absorbs enough energy, it should be able to escape from the metal. That is, if light is a continuous wave. So the wave theory is telling us we can shine light on the metal surface for a long period of time, and the electrons in the metal surface will continuously absorb energy from different photons of light, and when they gain enough energy, they will be able to leave the metal surface. Unfortunately, this does not happen. Experiments have shown if you shine light on the metal surface for whatever period of time, as long as light has a lower frequency, photoelectric emission is not observed. No electrons are emitted from the metal surface. So this now brings problems with the wave theory. But if you recall from your knowledge of AS physics, that energy carried by a wave depends on the amplitude and its frequency. Energy depends on the amplitude and the frequency. This means that even if we have a lower frequency wave, its energy can be boosted by increasing the amplitude. In this case, it would be increasing the brightness of the light. Because remember, intensity is directly proportional to amplitude squared. So if light is a wave, it has two major properties. Waves have two major properties, amplitude and its frequency. And the energy of a wave depends on the amplitude and its frequency. So even if the light has lower frequency, it should be able to cause photoelectric emission. Because if it has lower frequency, we should be able to increase the amplitude by increasing the brightness. If brightness is intensity, it means increasing brightness means increasing intensity, which means increasing brightness. Increasing the amplitude. So the wave theory is predicting that if we were able to increase the amplitude of a wave, even if its frequency is low, photoelectric emission should occur, but unfortunately it does not happen. So this now starts bringing questions. Is light really only a wave? So according to the wave theory, we ought to be able to cause photoelectric emission using any frequency of light, provided we make it bright enough. That is according to the wave theory. we should be able to eject electrons from a metal surface, even using lower frequencies, as long as we can make light to be bright enough. Unfortunately, this was not observed. Alternatively, it predicts we could use less bright light and shine it on the metal for a longer period of time, because light is a continuous wave according to the wave theory. So if it is a continuous wave, if we shine it for a long period of time, then the electrons in the metal surface will continuously gain energy until it is high enough for them to be ejected from the metal surface. Unfortunately, all this does not happen. All the predictions of the wave theory do not happen in real life. All this does not happen. So, the classical wave theory of electromagnetic radiation leads to the predictions that whether an electron is emitted or not should not depend on the power of the incident radiation, or should not depend on the power of the incident wave, that is, on its intensity. Remember, intensity is power per unit area. So it is predicting that whether an electron is ejected from a surface or not, it should not even depend on the intensity of the incident radiation, should not even depend on the power of the incident radiation. A very intense wave of any frequency should cause a photoelectric emission. A very intense wave of any frequency should cause photoelectric emission. So intensity equals to power over area, and power is equal to energy over, so this will be energy over time, then times area, and the energy of the photons equals to hf over t times A. Let's put an n here for the total number of photons. So it is telling us that whether an electron is emitted or not should depend on the power of the incident wave, that is, on its intensity. A very intense wave of any frequency should cause photoelectric emission. Whether the frequency is low or it is high, as long as the wave is very intense, the classical wave theory is predicting that a very intense wave should cause photoelectric emission. Whether an electron is emitted or not should depend on the power of the incident wave, that is, on its intensity. A very intense wave of any frequency should cause photoelectric emission. And if that is true, then the wave theory is also predicting that the maximum kinetic energy of photoelectrons should be greater if the radiation intensity is greater. That if we increase the intensity of the radiation or the incident radiation, that is, if we increase the wave power, then the maximum kinetic energy of electrons should be greater. And it also tells us there is no reason why photoelectric emission should be instantaneous. But yet, experiments show that whenever photoelectric emission occurs, it occurs instantaneously. So, these predictions based on wave theory do not match the observations. A new approach based on an entirely new concept, the quantum theory, was used to explain the findings of these findings. Observations from real experiments show that there is a minimum frequency that the incident radiation must have in order to release electrons from the metal surface, and we have just called this minimum frequency the threshold frequency. No matter how intense or for how long it is used, does not produce photoelectrons if it is below the threshold frequency. No matter how intense or for how long it is used, it does not produce photoelectrons if below threshold frequency. That is what is actually observed. But for the wave theory to just predicts that there is no need for the wavelength for the frequency to be above any certain value. Even low frequency waves or even low frequency radiation should be able to cause photoelectric emission as long as it is intense enough, or as long as we can shine it onto the surface for a long period of time. But just like I mentioned, this is not observed. It does not happen. There is a minimum frequency below which electrons cannot be released. There's a minimum frequency which the incident radiation must have in order to release electrons from the metal, and this is called the threshold frequency. No matter how intense or for how long the radiation is used, it does not produce photoelectrons if below the threshold frequency. So, we also mentioned that the threshold frequency is a property of the metal plate being exposed to electromagnetic radiations, and so it varies from metal to metal. So, the threshold frequency depends on the metal. In this lesson, we have used the zinc plate as an example. Different metals have different threshold frequencies. So just like I mentioned, you may use ultraviolet to cause electrons to be emitted from a zinc plate, but ultraviolet light may not cause electrons to be emitted from platinum. So different metals have a different minimum frequency above which photoelectrons can be emitted. So the wave theory has failed in so many ways. It is just says there is no reason as to why we should mind about photoelectric emission being instantaneous. They predict that the maximum kinetic energy should be dependent on the intensity, which is not true. They predict that even if we use low frequency electromagnetic radiation, electrons will be emitted as long as the wave is intense enough. In other words, that whether an electron is emitted or not, it should not depend on the power of the incident wave, because power is energy over time, and energy of a photon is hf, is telling us that a very intense wave of any frequency should cause photo emission. Yet experiments show that even if the wave is intense enough, as long as its frequency is below the threshold, even if we increase the intensity, nothing is observed. But if the threshold is above, if the frequency is above threshold, increasing the intensity would increase the kinetic energy of the photoelectrons emitted, which would increase the stopping potential. Increasing the intensity only affects the photocurrent as long as the frequency of the incident radiation is above the threshold. Let's explore more about the photon theory or the quantum theory in lesson 3. Until next time, bye bye.
At 29 and I find myself wondering, what did happen to the last 10? Ran away with my love last summer, and never turned back again. It's kind of funny that the more we pass time, the more I witness as I rewind.